Okay, now for your test, again, I'm going to give you the flow chart. So make sure when you're doing homework, dry labs, etc., have that out. Get used to using that. That'll be your best friend. And you don't have to bring it with you for the test. I'll supply it. And we get into unit 2, I'm going to have a modified one. Basically, it's going to be those reactions plus unit 2 reactions. Okay, and remember the little O stands for oxidation. So we have an alcohol here being oxidized. Remember, there are 3 kinds of alcohols: primary, secondary, tertiary. Tertiary alcohols have no hydrogens on the carbon that the hydroxyl group is on, so it cannot be oxidized. It can only oxidize primary and secondary. So what is this one? Is this a primary or secondary? Number 1 up here. If it's on the end, what kind is it? Primary. It's in the middle, it's secondary. So secondary alcohols have one hydrogen there. That means it can be oxidized once. So remember, in organic chemistry, when we talk about oxidation reduction, oxidation is losing hydrogens. In 305, you talked about oxidation is losing electrons. And reduction is gaining hydrogens or gaining electrons. Okay, so we've got to name this guy. And it's a 1, 2, 3, 4, 5. So it's a pentanol. On carbon number 2, counting from right to left. So when we oxidize a secondary alcohol, we end up with a ketone. So that's the hydrogen there that goes. You just have to say ketone. As a harbinger of what's to come, ketones are labeled O-N-E as the functional group. So that would be a 2-hexanone, if you were to name it, unit 2 naming. Okay. Now, if you look at your flow chart, it's on the bottom right whenever we start oxidizing anything, particularly alcohol. So this is a secondary alcohol, as well as this. So in this case, this is going to be a cyclic 6-membered ring. So it's going to be a cyclohexanol. And whenever we have a functional group on a cyclic ring, that's always defined as carbon number 1. So we could say 1 cyclohexanol or just cyclohexanol. Either one is fine. If you like to be consistent, put the 1 there. But most of the time you'll find textbooks that leave the 1 off because it's by standard that by definition the function is carbon number 1 because you got to have the lowest number. Any other carbon would give a higher number. Okay, so secondary alcohol, same thing, converts to a ketone. Now this one, interestingly, is a tertiary alcohol. As you remember, carbon has 4 bonds, and right now there's a CO bond and 3 carbon-carbon bonds with no room for any hydrogens. So that means no reaction. Now, if this was a primary alcohol, this would be 1-pentanol, primary alcohol. When it gets oxidized, it goes to the aldehyde. And because there is a hydrogen there, with the aldehyde, it can be oxidized once again, and then it goes to the acid. Carboxylic acid. And that would be called a pentanoic acid. That's unit 3 stuff. So again, the key on oxidation is losing hydrogens. So we have ethanol here. Two-carbon primary alcohol gets oxidized. And this is a process in your liver, biochemically, that your liver detoxifies alcohol. First, it's oxidized to the aldehyde. Then it's further oxidized to the acid. Now, the enzyme that do that is alcohol dehydrogenase. Dehydrogenase means it loses hydrogen, and it's oxidizing. This enzyme here, the second one, is called aldehyde dehydrogenase. That's the one that's more important than the first one. The first one, everyone's got a lot of that. The second one, it's limited based on your genetic makeup. Some cultures that have had alcohol introduced into their culture later have less of this than cultures that have had it longer. For example, Northerners in Europe have had alcohol dehydrogenase in their system for millennia, multiple millennia, because the people that don't have it die off and they don't multiply. So it just depends on your genetic makeup, whether you can detoxify alcohol or not. I mean, some people just have, regardless of your genetic makeup, you just have a defect and you can't produce alcohol dehydrogenase or aldehyde dehydrogenase. Okay, right? So here we have an alcohol, secondary alcohol, and at sulfuric acid or an acid environment, 180 degrees. Okay, that's going to produce an alkene, but it requires kicking off water. So where's the water? One water is here. Another water is there on an adjacent carbon. Okay, because there are two waters available, that means theoretically we're going to have a mix. And by the way, you have to, of course, name it as well. So this is going to be cyclohexanol. After it kicks out the water, it's going to end up being, so it's double bond is going to be on either side of the OH group. So here, going to be one. And that's going to be the other. Now, are those different molecules? Maybe one of the two, right? No, they're the same molecule. So there's a mix. It's just the molecules you make look the same. But always expect a mix whenever we have creating an alkene from alcohol. So they're both cyclohexene. Now, if we lower the temperature from 180 to 140, then we create an ether instead. It requires, excuse me, it requires lots of energy to get it to that alkene because alkenes are less stable than alcohols. So when we go from stable to unstable, we got to put a lot of energy into that system. Otherwise, it won't happen. If we only put 140 degrees in there, then we're going to get an ether. And that's where the OH groups hook up. So we have cyclohexanol forming dicyclohexane ether. Okay, so we have a secondary alcohol now. Back up to 180 degrees. Means we're going to form an alkene, but we need to shed water. There's water. And there's water. So again, we're going to get a mix. So it's 1, 2, 3, 4, 5. So we're going to get a double bond on either side of the OH group. So this is going to be, it's a 5 carbon, 1, 2, 3, 4, 5 carbon secondary alcohol. So it's going to be 2 pentanol. And this is going to be So this is going to be 2-pentene. And this will be 1-pentene. Which is more stable, left or right? Okay, let's look at Markovnikov's rule, counting terminal hydrogens. Okay, we have 3 here, 3 here, so that's 6 hydrogens. And we have 2 and 3, 5 hydrogens here. So right away, we know Markovnikov is going to favor the one on the left. Symmetrically, okay, the one on the right is lopsided. The one in the middle is slightly lopsided, but not as much. So symmetrically, it's going to be favored. More in the middle. It can't be exactly in the middle. We need an extra carbon to do that, but yeah. So always do 2 tests. Markovnikov sometimes will give 6 hydrogens, 6 hydrogen for both structures. So it doesn't tell you anything. And then go look at symmetry. And sometimes symmetry is toss up as well. In that case, if I had a problem like that on the test, I would mark, I would not mark either one incorrect if both tests were negative. So whatever you put down, I would be fine with. Okay. All right. So we start with this guy and we end with this guy. What's going on? Added an oxygen. In fact, we added not just an oxygen, we added a ketone. So if you look on your flow sheet on the bottom, how do you make a ketone? Of what? Perfect. Oxidation of a secondary alcohol. That's how you make a ketone. So that means we have an intermediate compound of a secondary alcohol. Now, can we make an alcohol from an alkene? We do it by adding water and an acid. So let's start, okay? So that water is going to add across the double bond, and you're going to get a mixture. And get that. Plus that. So this is a primary alcohol, secondary alcohol. And what do we need to make that ketone? We need the secondary alcohol. So we're not going to worry about this guy here. We're going to use this guy. Oxidize it. So as a synthetic chemist, I have a problem with this process. Problem is it gives me a mixture. So as an intermediate process, I've got to then purify my mixture, get rid of the primary alcohols, keep the secondary. I could do that with a whole bunch of processes. You can do it by crystallization, you can do it by precipitation, you can do it by distillation, just a whole bunch of different techniques. But whatever the technique is, we're isolating the secondary alcohol. And by the way, most of the time spent in a lab as a synthetic chemist is purifying your product, trying to find something unique about that product so you can somehow isolate it from the other stuff, whatever that may be. Okay, so now we're going to take that secondary alcohol, run it through an oxidation process. So we end up with that ketone. Now, was everyone able to follow my steps and rationale? Doing it on your own is a lot harder than following with me. So that's just one of those deals and levels of learning. The level up from that would be trying to teach your buddy this process. So there's 3 levels of understanding. You can follow me, you can do it on your own, or you can teach someone else to do it. Okay. So are there any questions about this worksheet? Okay, so let's do another one. Okay. If I give you the structure, you give me the name. If I give you the name, you give me a structure. All right. Octanol, 1 octanol. Okay. 8 carbons long. The OH group is on carbon number 1. And it's primary because it's on the end. 3 propyl 1 heptanol. Heptanol is 7 carbons long. 3-propyl 1-heptanol, and it is also primary. Why is it not an octanol? I just counted 8 carbons for the backbone. Why is it a heptanol and not an octanol? The backbone has got to include the group, the hydroxyl group. If you count 8, it doesn't include it. So if we go that way, that's 8 carbons long, but it doesn't include the hydroxyl group. Three hexanol, 6 carbon. And that would be a secondary because this is in the middle. Now, it's important to be able to recognize whether these are primary, secondary, because that'll determine whether they can be oxidized or not. Primary can be oxidized twice, so it goes alcohol, aldehyde, acid. The secondary alcohol can only be oxidized once because there's one hydrogen there. Here, there are 2 hydrogens. So it goes from secondary alcohol to a ketone. Two methyl 2-butanol. Okay, butanol's 4. And that would be a tertiary alcohol. And those are also in the middle, but have no hydrogens. And then 1,2-ethane diol. Diol means 2 hydroxyl groups, 2 carbons long. Oh, I forgot the other one over here. Number 5, 2-ethyl 1,3-hexane diol. So hexane, 6 carbons, diol. Okay, so we're going to go, and it's on carbons 1 and 3. And 2-ethyl. So that would be 2-ethyl 1,3-hexane diol. One 2-ethane diol, 2 carbons long. Okay, so here's a structure. Let's name it. 1, 2, 3, 4, 5, 6, 7. So that's going to be a heptanol on carbon number 2. I'm sorry, what? Yes, right to left. Okay, so we have 2 methyls, 3 methyls, and an ethyl. So methyl, 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 and then ethyl. Okay, so on carbon number 3, counting from right to left, is the first ethyl group. And then on carbons 3, 6, 6. Trimethyl 2-heptanol. Now, number 8 is kind of goofy. That's one backbone. That's another backbone. Both the same length, so it doesn't matter whether it's yellow or green. So let's use the green one. 1, 2, 3, 4. So that's going to be a butanol. And it's a 3 hydroxyl group butanol on carbons number carbon number 1, carbon number 2. And then as a branch, we have a alcohol branch. That's on carbon number 2. And we haven't talked about an alcohol being a branch. So I would so I would not have a problem like that on the test, by the way. So it'd be 2-methyl hydroxy, 1,2-butane diol. And again, I would not have that on the test. But the way you'd name the branch would be a methyl hydroxy or an ethyl hydroxy, something like that. Okay, number 9, 1,2-cyclopentadiol. So it's a cyclic compound. Okay, and we have 2 alcohols. And number 10 is very similar. Okay, we have we have 3 hydroxyl groups, so that'd be a triol, and they would be on carbons 1, 2, 3, 4, 5. So it'd be a 1, 3, 5, cyclohexane triol. Let's see now. This is primary. These are primary and secondary. Number 7 is secondary. Number 8 is, got anything you want? Primary, secondary, tertiary. These would be secondary, and these would be secondaries as well. Now, is it helpful when I go over these problems? Okay, all right. Now, your focus this weekend, I would recommend that you spend more than half the time studying on reactions, like 60% of your time, even 65%. The rest on naming. Because FYI, 15 years of teaching this class, everyone has trouble with reactions. Okay? And have your flow chart in front of you. Okay, so here we are. This is on alkenes. This is naming. And then we have reactions. Sometimes we have a geometric isomer, which would be a cis or trans. Okay, so we have 1, 2, 3, 4. So that would be a 4-carbon alkene. Two, 3 butene. Carbon number 2 is also 2, 3 butene. The difference is geometric isomers. So this would be cis, this would be trans. Remember, cis, like sisters, are close together. Of the two, which do you think is more stable, cis or trans? We have a cis here. What did you say? You said trans. We're well covered. Okay. Remember we talked way early in this class on steric hindrance? Yeah.
I got trans to butane and cis to butane.
Oh yeah, excuse me, there's no, and you did it correctly, by the way. There's no 3 here. It's just 2. Thank you. Okay, now let's look at this guy here. Which has more room, the trans or the cis? Basically, which are farther apart, the trans or the cis? trans. So the trans would have less steric hindrance. In other words, they're not bumping into one another. So in this case, the trans would be more stable than the cis. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be an octene at carbon 1, 2, 3. And we have two methyl branches on carbons 3, 4, 5, and 6. So it's going to be 5,6 dimethyl 3 octene. And notice it's in the trans position. Okay, on 4, 5, and 6 are benzene based. Now we talked very, very, very briefly about NO2 being nitro. That's a nitro functional group. And don't worry about that because when we do amines in that chapter, unit 3, that's when we're going to talk about nitro groups. So if this was something other than a nitro group, let's say chlorine, for example. Okay, so number 4. Now these are all based on benzene, not phenyl. Phenyl is only named as a branch. These are the benzene ring is the main molecule here. So the name is going to be derived from a benzene or a benzene analog. Now if it's got a methyl group on a benzene, it's called toluene. It's got an OH group, it's called phenol. So we have a methyl group here. That means the base molecule is a benzene with a methyl group, toluene. So this is going to be let's see, toluene. I think I spelled that right. Now, if you named it 2-chloro, 1-methyl benzene, I would not mark it wrong. I would put a sad face on it though. Because you basically got it. See, my purpose in having you name stuff, see something interesting? My coat was here. And Jerry Ochoa took it with him. I wonder where he is at this moment. Very interesting. The guy before us, he teaches 401 and good guy. Talks very fast, very fast. Okay, so this next one, okay, we have an ethyl group on the benzene. So
You said both would be partial credit.
Yeah, either one's okay. Um,
But you want us to put toluene.
well, theoretically toluene, yeah, because it's a methyl group on a benzene. But if you put those down, that, like I was saying, I would mark them fine. I would correct it, you know.
Okay.
Okay, so this is benzene with an ethyl group. So it's going to be ethyl benzene or 1-ethyl benzene. Either way is fine. I like 1-ethyl benzene because it's, again, consistent with our numbering, but it's totally optional. Our book will have ethyl benzene, not 1-ethyl benzene. And this last one is based on toluene again. So it's going to be So it's going to be 2, 3, 4, 5, 6. So 2,4,6 trichlorotoluene. Or you could also name it 2,4,6 trichloro 1-methyl benzene. Is that how you named it? Did you use nitro? What'd you put down for the nitro group, the NO2s? Oh, I thought you've already done these problems. Ah, okay. Yeah, as you should, because we didn't really cover it, so. Okay, so do those make sense? Particularly the cis and trans? Okay. So here we have number 7, we have hydrogenation. Hydrogenation is putting hydrogen across the double bond. And what's missing there? Look on your flow chart. What's missing? The way it sits there, nothing will happen. I shouldn't say nothing. It'll take maybe 100 years or so for something to happen. Extremely slow reaction. That's why they need something else there to help it along. What's missing? Look on your flow chart. What's missing? PT. We need a metal catalyst. Otherwise, it's a super slow reaction. Now remember, catalysts speed up a reaction and they have to be regenerated. So in other words, we don't use up the platinum. It's just there to act as a mechanism so the hydrogens can stick to it and the what molecule is that? One, 2, 3, 4. The pentene can stick to it as well. Okay, so we need, usually it's platinum. Sometimes it's chromium wire, magnesium. There's a lot of metals that work fine here. But frequently, if the lab can afford platinum, they use platinum. This platinum is very, very, very stable and can be reused a bunch of times. Okay, so we have 1, 2, 3, 4, 5. So that's going to be pentene, 1 pentene. And what's going to happen is the hydrogen is going to go across the double bond, giving us pentane. Okay, number 8, the chlorine gas, Cl2, is going to go across the double bond. So this is going to be 2-methyl. One pentene. By the way, she goes to the tutoring center and the library. And does anyone else? I know you talked about it. Did you go over there? Yeah. So if you want a tutor, and it's free, free's good. And if she helped you, yeah. So I'm sure she's clearer than me. So anyway, that's another resource for you. Also, Organic Chemists online on YouTube is another good tutorial source. Another good tutorial source, assuming you've had 2 or 3 cups of coffee, is Khan Academy. It's very thorough, but a little on the dry side. Like, oh. So if you can't sleep at night, go to the Khan Academy. So those are some of your resources. And also, hopefully you're in a study group. That helps a lot too. Okay, so let's name this guy. Okay, so it's 5 carbons long. One, two, three, four. Not, it's 4 carbons long, not 5. I'm sorry? Yes. Yeah. And when you first time you said it, I didn't. Yeah, I didn't get the halo part. Okay, so we need 4 carbons long. So it's going to be 1, 2 dichloro 2 methyl butane. And the Br2 is going to add across the double bond the same way. This is going to be a cyclobutane. And you could say 1 cyclobutane or just leave it as cyclobutane. That's going to add across the double bond. So it's going to be 1, 2 dibromo cyclobutane. No, the double bond's gone. Yeah, because we added the 2 BRs across it. That's why it's butane. What you start with is a butene because it still retains the double bond.
Yeah.
Oh yeah, it should be butene. Yeah, butene. Okay, and we're going to add. So this guy here is 2 methyl 2 butene. So 1, 2, 3, 4, 2 butene and 2 methyl. Chlorine goes across there. So this is going to be um, 2,3 dichloro 2-methyl butane. So all the homogeneous Cl2, Br2, H2, when they go across the double bond, there's no mixture. When you get the heterogeneous ones like HCl or HOH, water, then you look for a mix. I think on the flow chart I said expect mix, yeah. And you get a mix 90% of the time. Sometimes you end up with creating the same molecules. So you have a mix, it's just the molecules look the same. Okay, so we have cyclopentene with water. Okay, cyclopentene will look like that. And water is going to add across the double bond. And you'll see it either H plus or H2SO4, sulfuric acid. And so that HOH is going to add across the double bond. You end up with no mix because the two molecules you make are the same molecule. So these are the two molecules you make. But if you rotate one, it ends up being the same molecule. So there's no mix in this situation. There's a mix, it's just the molecules you make look the same. So this would be cyclopentanol or 1-cyclopentanol. Okay, and this guy here, number 12, we have HCl, heterogeneous addition to that double bond now. So we're going to expect a mix. So we're going to get 1, 2, 3, 4. This is going to be 1 butene. So one is going to be like this, and the other is going to be like that. So, which is more stable? One on the right. Okay, we look at symmetry. The one on the left is stuck on the very end, so it's very unsymmetrical. And we look at Markovnikov. So we have okay, 5 hydrogens, 6 hydrogens. So this one wins out. So let's do this one down here. So this is going to be a 1, 2, 3, 4, 5. So it's going to be a pentene. Starting on carbon number 2. Then we have a methyl group on carbon number 3. So we're starting numbering right to left. So we're going to get a mixture because again, HBr is heterogeneic. I'm going to get a Br here. And a Br here. Okay. So we have Markovnikov, symmetry. So left or right? Which is more symmetrical, first of all, left or right? The one on the left is nice and balanced, where the Br is right in the middle. So symmetry, yes. Now, this is where Markovnikov doesn't work because this is 3, 3, 3, 3. So symmetry is the main driving force in this one here. And then we need to name these guys. So this is going to be a pentane at 3-bromo, 3-methyl. And this one's going to be a 2-bromo, methyl. Okay. All right, we have one more to go. So we're starting with so we have 2-methyl cyclohexene, be 1, 2. Okay. Throw in some water and some acid. So the water is going to add half the time one way, half the time the other way. So we're going to get a mix. Now this is a good example of, it's hard to tell which is more stable. They're kind of both the same. So in this situation, it doesn't matter which one you circle. Markovnikov, same number of hydrogens. Symmetrical wise, probably the left one's a little more symmetrical. Maybe the right one, I don't know. It depends on your perspective. So this one, Okay, so we have 2-methyl. cyclohexanol. And here we're going to have 1-methyl. And you could put a 1 here if you wanted to. Okay. So these are good test examples. These worksheets we went over today. So make sure you understand these well. Now, next week is another dry lab. We have one more after next week in the middle of the semester. Your first wet lab is going to be following week, week 4. Now, it's a long lab. You're going to be having to bring, you're going to be working in groups. And each one of you just bring an orange or a tangerine, something, or a grapefruit, something lemon, something citrus. And we're going to be doing, something called a steam distillation. We're going to extract the essence of what makes that smell and taste like a citrus. Then when we make soap, we're going to be putting that essence back into our soaps. So our soap will smell citrusy. It's kind of cool. So on probably Tuesday, I guess, I'm going to go over a wet lab write-up. I'll do a video of it also. And then we'll start unit 2 on Tuesday. Going to be in aldehydes and ketones and carbohydrates. Okay, so any questions about anything? Yeah.
Did you say it was okay to name it 2,4,6-trichloro-1-methyl-benzene? Or is it not a benzene?
It's toluene
It's a toluene.
because of that methyl group there.
Can I put methyl toluene?
No, that would be redundant.
Okay, don't put
Either
methyl.
put 1-methyl-benzene or toluene.
1-methyl-benzene, so it's either, I'll put it in parentheses. High school toluene. Oh, TO.
TOULUENE. I have to sound it out in my head. Okay, so it's sounding like me with my cough. Thank goodness I'm over it. You guys, I couldn't talk more than 10 minutes without having a coughing fit for 10 minutes. It was gross. So I had to go to the doctor twice. First time it didn't work. So, okay, so any more questions? Okay, so that's what I have for you today. And definitely spend time this weekend. And remember, we're having 5 tests. So if you blow one, you still have 4 more to balance it out. Last semester, I just had 3, and it was a killer.
When you were converting not the toluene, the alkenes into their reactions, that you were putting the elements on either side of the double bond. That's correct, right?
Mhm.
On either side of the double bond. Okay. Let's make it.
So if you had 2 CLs, you'd have a CL
One side of
No, on both sides.
on both sides.
You had HCl. One side we get an H, which you don't see because it's a line drawing, and Cl, and then ClH. You know,
Definitely gonna work with the two now. I need to understand that.
so you have a series. You know, this is going to be, and think of this instead of as H2O. Oops.
Thank you.
Yes, exactly. Because then you can see the H separated from OH. H2O, yeah,
And you put them on either side of the double bond.
and then flip it. Yeah. So instead of HCl, you have ClH.
Okay.
And those are the two that you end up with. You do the same thing when you have ClCl. It's just you can't tell the difference between the Cls because they're both Cls. Now, if you had one marked, like with a radioactive or something like that, then you'd see, then you'd have a mix. But since it's the same, there's no way to tell. You're doing well, though. That tutors really helped.
The last one. On another problem, we started before. So does it start? 'Cause I know it has to be on one of the ends of the double bond.
Yeah, you know, it probably would, I see what you mean. Yeah, so it'd be like, yes,
That's slip. Right there.
ah, yes, this is what he was looking for. Thank you.
Sufficient. That's like must be like that.
Yeah, well, and this is magnetic as well,
Yeah.
so it sticks. Well, I'm gonna trade them for my coat. Yes, we have a dry lab, only I left them up in the lab. So I'll be up there shortly though, because I'm gonna let this run up there.
Yeah.
Okay, the problem with this though is the numbering starts at the 1 and goes to the 2.
Where was it?
Oh, did you grab my coat also?
Was
was
that
on-
mine?
That was my,
Oh my God.
and I found this.
Where was it?
Well, it's magnetic. It was stuck right in here. Gee,
Let me go get you.
isn't this funny?
So I think I have the same exact code as you do, or at least it's like very similar. So I'll go get it from my office.
Thank you. Okay, so talking about scattered. Okay, so you number going into the double bond. So this would be like that. So to number it would be one methyl. Actually, the way you do it would actually be better. The numbers would be lower. So it'd be 1 methyl cyclohexane.
So, but either way is fine. The way.
For our class, yes.
Okay.
Yeah, because the purpose of, let me stop this and start the rendering process.